Okay, let's get started. So welcome everyone to another lecture in our ID 5130 parallel scientific computing course. Okay, so in the last lecture we kind of started off with MPI programming. Okay, so in today's lecture let us look at deep into the send receive function calls in MPI, and also how does the matching of the messages happen, as well as essentially what exactly happens, how does this send receive exactly function, and also some potential mistakes or pitfalls, and then what are the consequences. Okay, so how to kind of avoid them. All right, so we noted that in message passing interface the data exchange between different processes, right? We started off calling the threads as or cores as different processes. Between different processes happens using send receive function calls, right? So you basically identify what data needs to be sent to the other process, and then the other process will receive the data, and this is achieved using send and receive function calls, right? If you look at the prototype as we the function definition or function prototype for these send and receive, we also looked at in the last lecture, so I'm kind of repeating that. You have basically an integer return type, and you have MPI send, and we know that the S needs to be capital here, first letter after underscore MPI, and then we have MPI send. It basically has 6 arguments, right? The first 3 correspond to the message information, and the last 3 correspond to the destination of the message, right? Essentially information about the destination process. So we basically have a buffer, right? That is basically the message to be sent. So you have the message buffer pointer, right? And this will be basically void star. Now why is it void star? Can you think of it? Why is it void? Why is it not int or float or something? Okay, and then the other argument is the size of the array, right? Size of the buffer, so message size, right? Now because we are passing a pointer here and then the size, this memory has to be continuous, right? It has to be should be contiguous memory, right? Continuous memory, because that's how it will access it. Then the message size basically corresponds to the essentially length of the array that we are sending, right? Okay, and then we have, of course, the data type. For example, we might be sending 50 ints or 50 characters or 50 floats or 25 floats. Then the float, integer or character should be kind of specified using a MPI data type that is actually created by MPI. So MPI data type, you would have the message type, right? So this would be MPI int or MPI float and so on. Now that's about the message information, and then the about the destination. The other 3 arguments are about the destination. So that means you basically would supply an integer which will be the rank of the destination process to which this message has to be sent, right? And then you also would supply a tag, right? And this tag will essentially identify. This is to identify the messages or to match them. Okay, so you would supply some integer tag and you would specify the same integer tag on the in the receive function call, that is in MPI receive, so that these 2 messages can be matched and the information that you received will be on that process can be copied into that particular memory location. Okay, so and then after the tag you of course have to specify the communicator, name of the communicator. We have used the MPI communicator as the is the type of that particular communicator, and then we used you specify whatever the communicator. So we ended up using MPI com world, that is the default communicator created by MPI, right? So that is about the MPI send. Now the corresponding function call for MPI receive also has 6 arguments, plus it has an extra argument which is basically the 7th one is has a data type of a MPI status, right? That's kind of a pointer to MPI status. So let us see that also. So in MPI receive, what you have is you have the return type as integer, that is basically to know the successor of the process. So you have integer MPI receive, and then you would have again a void star. So you have the message buffer pointer. So this is again the continuous memory location into which the message has to be received, right? And then you would specify how many what is the length of the message that is being received, right? And then what type of the data that is being received. So MPI data type, you would have the type of the buffer, and then the last 3, the next 3 will basically tell again about where to receive the message from. So integer type, and then you have to receive from a process that has this particular rank. So this specifies the rank of the source process from where to receive the message, right? Okay, and then after the source you have of course the tag, just like in the MPI send. So you have the tag. Again, this tag needs to be the same as what was sent, so that these 2 messages will be matched, right? And then the next argument is the communicator. So you have MPI communicator as the data type, and then you have communicator. So again, this is com world or any other communicator that you would create. And then the final argument, we said that this is basically MPI status pointer, and then we have a variable of type MPI status pointer, right? That kind of points there. So we will see what or let's call it a status pointer. Okay, so we would allocate memory for this, and then that will be passed into the MPI receive. Okay, now we will come to what is this status little later. Okay, but before that, let us see how does message matching happens in MPI. Okay, so message matching in MPI. Pull it up a little. Okay, so this is message matching in MPI. Okay, so let us say we have a send function and a receive function, and it is written in a particular program like this. So basically we have a process A. So for example, we have process A, that is a particular process A has a MPI send call. So we have MPI send, and it calls it like this. It basically calls it as a you have send buffer pointer, and then you have send buffer size, right? And then send type, right? And then you have the destination. This is basically the rank to where it has to be sent, and then you have the send tag, and then the communicator. Okay, so basically this is the communicator. Okay, so let me call it as send communicator to be specific. Send communicator. Okay, that is how a process A calls a MPI send, and then we have another process B, okay, which has a receive function call. So let me put it as MPI receive, and then we have receive buffer pointer, receive buffer size, right? Then we have receive type. Okay, and then we have the source from where a message may be expected, and then we have the receive tag, right? And then we have the receive communicator. Okay, we have all these. Okay, now how does the message matching happen? So for example, the message sent by process A, if it needs to be received by process B, there are certain certain rules, or there are certain things that needs to be checked before it can happen, right? So a message sent by process A will only be received by process B if there is some matching that happens, okay? And that matching is basically, so the message sent by process A, or let me write it here. So the message sent by process A using the above MPI send function call may be received by process B using MPI receive function call, right? Okay, if and only if the following conditions are met. Okay, so what are those conditions? Those conditions are, first of all, the communicator has to be the same. Okay, that means the communicator for the send message and the receive message has to be the same, and after that the tag of the send tag must match with the receive tag, and then we also should have the destination here should be B, okay, and the source, let me use orange, okay, the source here, the source here, okay, so let me use orange now. Okay, so this source should be A, okay, only then. So that those are the first set of conditions. So let me write it here. So basically the send communicator should be the same as the receive communicator. That means both of them should belong to the same communicator, both the processes, and then the tag should match. So receive tag must match with the send tag, okay, and then the source here must be A, and then the destination here must be B. Only then the first phase of conditions are met, and the process sent by process A might be received by process B, okay, or may be received. So let me just write it here. Only if the receive communicator is the same, okay, I just use single equals here, but then that means that is the same as the send communicator, okay, and then we have the tags must match. So receive tag must be equal to the send tag, and then the destination specified on process A should be B, and then the source specified on process B must be A, okay. All right, so then however, I mean, essentially, as I said, these are kind of first set of conditions. However, these are not quite enough for successfully receiving a message, okay. So as a result, we have few more conditions that is basically on the message that is being sent, okay. Basically the first 3 pairs of arguments, that is basically on, that kind of depends on what is the type of the buffer and size of the buffer and the message buffer itself. So these 3 also play a role in determining the success of the message that is being sent and received. So how does these play a role? Basically, you have together with these conditions, the send buffer predicate, the pointer, and the receive, so it also depends on the receive buffer pointer, right, and then on the send buffer size and receive buffer size, okay, and then finally on the send type and the receive type. So there is also conditions that are imposed on this so that a message can be successfully received, okay. So the conditions, the remaining conditions are that the receive buffer should be at least larger than or equal to the send buffer. That means the size of the receive buffer must be larger than or equal to send buffer size. That means we should have at least whatever is the memory that is being sent is allocated or more than that is being allocated. Okay, so that is the first condition. The other condition is that the type of the variable that is received should be the same as variable that is being sent. So that means the receive type must match. Okay, so the receive type must be equal to the send type. Okay, those should also match. And of course, usually the amount of memory that is allocated is not checked here, only the sizes are checked, but then it is assumed that there is a memory that is allocated. Okay, essentially this this memory should be already available. Okay, should be already allocated before the function call, right? Well, if you don't allocate, what happens? It will give basically a segmentation violation at the time of accessing this memory location. If this kind of points to a null location, it's going to give a segmentation violation when it tries to write to that memory location. Okay, so before the function call. Fine. So essentially, these are the 5 conditions. The 4 conditions are here, and then the remaining 2 conditions. So these are the 6 conditions. Usually these are sufficient to say that the message sent by process A will be received by process B successfully. Okay, so these conditions are kind of sufficient to say that the message sent by process A may be successfully received by process B. Okay, I mean, assuming that there are no other issues with the network and other errors or something like that. Okay, all right. So that is about the matching the messages. Now this may kind of raise a few more questions in terms of what will happen if, let's say, if a particular process is receiving messages from multiple processes. Okay, let's consider an example in which we have a process 0. Okay, so let us say a particular process is receiving several messages from several processes. That means, let's say we have a process 0, I denote it as P0, is kind of assigning work to P1, another process P2, another process P3, and so on all the way to Pn-1. Okay, so this Pn-1 is the last process in the total communicator, and then it is assigning some work. Now P1, P2, and then will carry out their work, and then we don't know for how long they would carry out their work. They would carry out their work for some unpredicted amount of time. Okay, they will kind of do the work, and then once they finish, they are going to send this messages back to P0. Okay, they are going to kind of send the messages or send that details of that work back to P0. Now the only thing here is that the amount of time that is being taken by all the processes is unpredictable. Okay, let's say we are assuming that. Okay, I'm assuming that it is unpredictable. So P1 may take longer than P2, P3 may take longer than P2, and then Pn-1 may take longer than P2 but lesser than P1, and so on. Okay, so it's kind of unpredictable. But then P0 has to receive these messages. So of course what you can do is, if the work assigned basically to different processes is unpredictable, take unpredictable amount of time, therefore P0 has no way of knowing from where to receive the message first. Okay, because it doesn't know when will these finish, so it doesn't know whether should I wait. I mean, the way I have drawn, let's say P10 takes a very little amount of time, then P10 should be sending its data to P0 first, and followed by, let's say, P2, followed by Pn-1, then P3, and something like that. Okay, P1 and P3. But then if this is unpredictable, then P0 has no way of knowing in which order to receive messages, right? Now if you may think, okay, what about if P0 will basically receive messages in the order of the rank? For example, it will receive from P1, then from P2, then from P3, and then from Pn-1. Well, that is very much possible, and that is one way of receiving it. But what it doesn't guarantee is that, let us say, if you receive if P0 receives messages in the order of the rank of the processes, right? That is all right. However, let's say if Pn minus 1 finishes first, then Pn minus 1 has to wait until all other processes have finished, isn't it? And sent their data, right? Until all other processes have finished and sent their data before Pn minus 1 could actually send its data, although it has finished. But okay, so to avoid such things, MPI kind of provides a convenient way of receiving the messages with a particular tag. Okay, that tag is basically known as the MPI any source. Okay, so you could use MPI any source instead of in the receive message here, instead of specifying the tag as a particular source here, right? Instead of specifying it as source as A or something, you know, some other name here, you could use MPI any source here. Okay, all in capital letters, because this is a variable defined by, or a macro defined by MPI, right? So as a result, you can specify MPI any source. Basically, that can be this can be passed to MPI receive, and this basically tells that process 0 you know, can receive message from any process whichever is kind of sending it first. Okay, now of course you would not know the order unless it is received, so you have to kind of see how to again if you want to dig deeper and know what you know, which message which process has sent it, then you have to do little more work to find out that. But however, if you write it this way using MPI any source, then it would just basically receive message from any of the sources in the order as soon as they finish. Okay, so that means if I write this function, a small code fragment here, that means on process 0, right, on process 0, or you have this particular code, right? Basically on process 0, if my rank equals 0, right, then what it does is it basically receives messages. So receive for I equals 1, I less than or equal to, I mean just I less than number of processes, and I plus plus, right? And process is nothing but your communicator size, right? Number of processes you have, and then it's going to receive messages. So you say MPI receive, you receive basically your receive buffer pointer, then receive buffer size, then receive type, right? Then you have basically the source, which needs to be MPI any source. Then you have the receive tag, right? Then you have communicator, then you have the status pointer. Okay, so that's how you would use it. Then once you receive some data, you can of course call any other function that you would like to call with some whatever with the received buffer to manipulate or make changes to the receive buffer and things like that. Okay, so that is how you would use it. If there are multiple processes sending messages to process 0 in any order, and you would not really want to keep a particular process waiting, then you could use MPI any source as your wildcard. Okay, so that as soon as a process finishes, its message can be received by process 0 without keeping it waiting. Okay, now similarly, let's say if it is, you know, it is possible that a particular process may be receiving multiple messages with different tags from another process. Okay, let's say you have process A is sending out messages with different tags to process B. Okay, let's say these are the different tags. You have 100, 200, 300 and so on. It's sending out several messages to process B, and now process B actually doesn't know the order in which the tags are received, right? and it probably is not required unless, let's say we have a particular situation in which process B will receive these messages from another process with different tags, and the order itself really doesn't matter. Okay, that means then we don't have to worry about specifying the tags for these. Rather, we could use another wildcard argument that is known as the MPI any tag. Okay, and then process B will again receive these messages in whatever order they come. For example, 300 comes first depending on the unpredictable amount of work that particular process A has to do, then 200, then 100, and things like that. So that means instead of this receive tag here, we could even use MPI any tag. Okay, and that's going to basically enable the receive process to receive messages with any tag. Okay, so these are the two wildcard arguments that can be used, MPI any source and MPI any tag. Okay, fine. Now there may be some questions. Now, can these wildcards be used on both the send and receive process? No, it can only be used on the receive process. Okay, that means the conditions are that only a receive process can use a wildcard argument okay, such as MPI any source or MPI any tag. Okay, the sending process or the sender process must always specify the rank, or must always specify the destination rank and a non-negative tag. Okay, so tag that we have used should always be non-negative. Okay, then of course you also have only one more variable left, that is your communicator, and there is no wildcard for the communicator. Okay, no wildcard. So that means there is no wildcard argument for the communicator. Okay, that means you cannot receive a message, cannot be received from any other communicator that is available in the world. Okay, so argument for the communicator. So that means both the sender and receiver processes must specify the name of the communicator. Okay, okay, so that's a must. All right, so that is about basically how does the matching of the messages happens, and then the few wildcard arguments. Of course, we also still have one more argument which we didn't discuss till now, that is basically the status P argument in the MPI receive, right, which is basically the extra argument that is there, which was not there in the MPI send. Okay, all right, so what does this status P argument do? Now, before we go there, let us see if we can kind of think about what are all these wildcards trying to do. The wildcards are basically telling you that if you kind of think for a little while, that basically a message can be received by a MPI process, without essentially knowing the amount of data that is being broadcasted, right, that is being sent by the message, and also without knowing the information of the sender, right, who is sending it, as well as the tag of the message. That means even without knowing these things and the amount of data, right, the receiver can actually receive the message, right. That means then how does the receiver actually find out if these were specified? How does these things were actually found out by the receiver? Okay, now I think this needs to be a little more clear. Okay, so what I mean to say is that, so let us discuss about the status pointer argument, right, which has the type of MPI status. Okay, now this is important. MPI status, which is used in MPI receive function call only, right? Okay, now what I mean to say is that, okay, we let's go back to this thing. Okay, let's go back to the receive function call. Okay, so we have reached the receive function call. Now what I mean to say is that you have the message buffer, right, into which message will be, which is basically some continuous memory or array, and into which the message will be received, and then you have some size into which you hope that, you know, the message being sent will fit, and then you are again hoping that this will be the type, and then this particular process is expecting a message from this source. Okay, so that needs to be clear. It's only expecting a message from this source, but it really doesn't know whether the message is coming from a particular source or not. We are only saying that there is a message coming from this source, but then how does it know that it is coming from this source, right? How does this process know that a message is coming from this particular source, right? Okay, similarly we are saying that this is the tag which you have to match, right? But then the message itself that is coming should have another match to verify, isn't it? This tag should be matched with something else. Similarly, this source must be matched with something else, which is basically the data that is being sent by the MPI send. Okay, now where is that? The communicator, of course, needs to be also checked, and then so these things, that means you know, kind of draw a couple of questions in terms of saying that a process may receive a message without knowing these things, right? That means without knowing the sender as well as the amount of data as well as the tag of the message. Okay, but then by using the wildcards. But then how does it actually, if you don't use a wildcard, how can the receiver find out what these values are? Okay, so that is the question, right? I hope it is clear. We are specifying that this is the message, this is the particular type, and this is the, you know, sender, and this is the tag, but the message that is being sent should also have it written somewhere, so that this can be cross-checked before it actually receives it. Okay, so that means a receiver can receive a message right without knowing the following, right? What are the following? Amount of data in the message, okay, and the sender of the message, right? Because we are specifying that the message will be sent by some source, but that source we don't know whether it's actually coming from there or not, right? And then the tag of the message. Okay, now how does the receiver process find out about these things? Right? So essentially the answer lies in the last argument to the MPI receive, that is your status P. Okay, so this status P, which is basically a pointer to MPI status. So if you had declared something called MPI status as this is the data type that is provided by MPI, and then if you have a variable that is your, let's say, status, then this status is now, this MPI status itself is actually is not just a simple data type, it's basically a structure, right? When I say structure, this is a structure in C, okay, which will contain several data types that are packed together, right? So this particular structure contains a lot of information, and that information is basically nothing but the information that is required to cross check or to find out about these values. Okay, to find out how much is the amount of data that is being sent, who is sending it, and what is the tag that it is being coming with, that is contained in the status, that is received in the status, and this is being sent by the MPI send, basically by the MPI system. Okay, so we don't have to write it explicitly, but MPI system will send that, and then that will be received in the status argument here. Okay, so that is the idea. Now this MPI status should, depending on the implementation, should have at least 3 members. Okay, one of them is MPI source, another one is MPI tag, another one is the final one is MPI error. So that means the values can be accessed using just like any other structure. You can say status dot MPI source, right? That is basically who is sending the from who sent this message, and then status dot MPI tag is basically contains what is this tag that the sending process has been sending it with. Okay, that means these two of course have to now match with the source that we have written in the MPI receive command and the tag we have written in the MPI command. Okay, if that happens, that means then it is kind of authentic, right? It's basically coming from in the same communicator with this tag from this source, so it can be, the message can be copied into message buffer. Okay, so that is how the status P or status MPI status argument helps us match the messages. Now of course we have not discussed anything about the data, the amount of data that's being received, right? So the amount of data that is being received, right, is where is that? Now to answer that question, again we have to go back to this MPI receive. Again we say that receive buffer P is basically your amount of memory, the pointer to the base location here, and receive buffer size is only the number of elements, right? Not just in the receive buffer, but receive buffer size is basically the number of elements that we are planning to receive. That means this receive buffer P can point to a larger array, but receive buffer size can be only smaller than that. And then we are only, let's say, receiving 10 we are only receiving, let's say, 10 float values. Okay, so we have 10 floats, but then this 10 floats is what we have specified in this command. But then is what is being sent the same as this or not? That is contained in status P, and then that status P and that data is not accessible directly to a user. So you basically have to call another function by sending your status P as an argument to find out is the data that is being sent the same as receive buffer size or not. Okay, or it can be even smaller than that, right? Because receive buffer size needs to be larger or equal to there. That means and that function you have to call, if you want to know this, is MPI get count. Sorry, this C has to be lowercase. Get count. Okay, and you have to call send your status pointer address, and then you have to send what is the receive type, and then you would again send how much is received. Okay, so it will basically, depending on the receive type, the data that is being received will be divided by the receive type, and then it will tell you how many floats or ints are received. Okay, are being actually not received, are sent or were sent by the MPI send function call. Okay, so that is how these data can be cross-checked by MPI receive command, and it can be used to again match the messages. Okay, I mean, of course we can also check that using the status P, but in case we do not want this thing, then we can use we can say MPI status ignore, and if we don't want to do that, we can also do MPI status ignore as a wildcard argument, and we would not need to allocate or define this variable anymore. Okay, if we do this then, but it's kind of a good practice if you want to cross check to use MPI status and then use the structure to do it instead of using this wildcard and to not have access to that. Okay, so that is about the essentially the status P argument and all other arguments in the send and receive function calls. Okay, now let us look a little bit into the exact process of MPI send and receive. So basically the the functioning of MPI send and receive. Okay, so essentially what will happen, functioning of MPI send and MPI receive. So essentially what will happen when we call this MPI send function, and what will happen when we call this MPI receive function in little bit in detail. Okay, so most of these details kind of depend on the particular system. However, we will be able to draw some general conclusions on the behavior of MPI send and receive. Okay, and that is what we're going to see now. Okay, so essentially whenever there is a MPI send function call, what does the send process do? The send process, okay, when it encounters a MPI send function call, it will basically assemble the message. So it's going to assemble the message. Now this message is more like a kind of an envelope, right? So we have some message that is let's say, so we have some message here. Now this message needs to be put in an envelope, right? And that envelope is what will be created by the by assembling the message. That's what the sending process does. So it will basically put an envelope on this, okay, and then it's basically going to prepare it with the essentially the data that is inside plus the addresses, right, to where it should go and all those things, right? So about the actual data, and then when you say addresses, it's basically going to write the destination, and then the tag, and then the source who is sending it, and then the communicator, right, and then the size of the message, etc. That means a part of this addresses is what is being received by the status, as you just learned about. Fine, so that is what the sending process will do. Now once the message is assembled by the send process, then the send process may do either of these things. It may buffer the message, or it may block the message. Okay, so once the assembling is done, the sending process may buffer it. If it buffers it, then what happens is that the message will be sent to the MPI system, the internal storage of MPI system, and once the MPI system internal storage takes over the buffered send information, then the MPI send will return. Okay, so MPI send function call will return. So once it returns with a buffer kind of thing, then what it means is that the message is kind of buffered, and the send data that we have used may be reused. Okay, so we have used some send buffer P that may be reused because this message is now copied to some internal storage of MPI system, and as a result MPI send has returned, and that send buffer P may be reused. Okay, now what we are looking at is using MPI send is basically the block. In the other way, MPI message send can be blocked. If it is blocked, MPI system will wait until it is ready to transmit. Okay, so in this case MPI send will not return immediately, rather it will wait until the message is being is kind of transmitted. Okay, so this is what it can, either of the things that can happen. And then what about the MPI receive? Unlike the MPI send, MPI receive doesn't have a buffering thing, at least in MPI send. MPI receive in this particular function call, and it will always blocks until a matching message is found. Okay, that means a call to MPI receive will only return, right, it will go to this return will happen only when there is a particular matching message is found and the message has been received. So that means when MPI receive returns, we know that there is a message received in the buffer, right? In the buffer that we have asked it to put in there, right? Now, of course, assuming that there is no other error. If there is error, of course, there will be some error and the buffer would contain nothing, okay? I mean, other than this, there are also other, so this kind of what we are looking at is basically known as the MPI send and receive. These are known as blocking communication, okay, in which MPI send will always block and it will wait until it is ready to transmit, and MPI receive will always wait until a matching message is found, okay. There is also something known as non-blocking communication, which we will try to learn later, in which MPI send will buffer, will buffer, and similarly MPI receive also will doesn't have to wait, rather it will basically check that there is a matching message and then it will kind of return, okay, without actually receiving the message. So such kind of communication is known as non-blocking communication, and we will learn about it a little later. Okay, now what are the consequences of this kind of a blocking MPI send and MPI receive behaviors? Okay, so what this means is that we have to kind of make sure we have matching MPI send and receive function calls, okay, that is very important. Okay, and also let us also see a few things about the MPI standard, and MPI also requires that the messages sent by a single process, by the same process, be non-overtaking. That means if a particular process sends a message, let's say process A sends a message 1 followed by message 2, then when this is received by process B, first of all, essentially a provision will be made to receive a 1 first on process B, okay, and only that process 2 will be provision will be made to receive process B, okay. That means the messages sent by a particular process will be in a non-overtaking fashion, will be received or will be made an opportunity to receive in the non-overtaking fashion, okay, if that is being sent from a same process. However, if they are sent from different processes, if different processes send messages, then MPI doesn't impose any restrictions. That means, let us say you have two processes, okay, process A and process B are sending information to, let's say, process C, okay. Now let's say process A is residing on the same computer, okay, whereas process B is somewhere else. Let's say this is sitting in the United States or something, and then process B happens to send let's say a message few, let's say, milliseconds before, okay. However, we know that it's however, we know that the process A, being sitting on the same computer, would reach process C faster, although it is sent later, right? As a result, it doesn't make sense to wait for process B to arrive, because although it was sent a few milliseconds before, it has to travel a long distance through the fiber cable, and then it has to receive process B. As a result, MPI would not impose any restrictions. This is because MPI cannot impose restrictions on the network, okay. So that means MPI cannot impose restrictions on the network, right, on the performance of the network. So as a result, there is no guarantee that this will be a provision will be made to receive the message sent by process B before the process A. Okay, so that is about the order in which the messages may be sent and received by different processes, depending on whether the same process is sending or different process sending it. Okay, now in this context, let us go back and look at some of the mistakes or pitfalls that you may run into because of the blocking communication that we have seen, in which, you know, essentially some potential mistakes or pitfalls while writing code is that we should always make sure that there are matching send and receive function calls. Okay, for example, let us say you write a particular code in which there is a, let's say there is a process A and there is process B. Okay, and then you have written in your code, the way you have written is you have written an MPI receive. Okay, however, you forgot to write MPI send. As a result, process B would kind of wait forever to receive a message to be sent by process A, which it will never send because there is no MPI send. As a result, process B will hang. Okay, so that is kind of one mistake you should avoid. And similarly, you may forget to write an MPI receive, and you probably have written an MPI send message. And if MPI send happens to be a blocking message, then what happens is that then this process A would hang, right? It would probably it would hang trying to send the message, right? Because there is no matching receive. As a result, this would basically hang, right? And then if MPI send happens to be a buffering type of MPI send, and there is no matching MPI receive, you know, you forgot to probably write and you introduced a bug, then what happens is that then this MPI send, if it is buffering time, then this message you have sent may be lost, right? Because it is buffered to something, and then that is never received by MPI receive. Okay, that means you should always make sure that there is, for every receive, there is a matching send. Okay, so when you code, always make sure every receive has a matching send statement. Okay, similarly, you should also ensure that the tags are matching between the send and the receive commands, and then the also you should make sure that the ranks are put in correctly for the destination and for the source in the MPI send and receive. Okay, so for example, let's say if you by mistake if you put the destination rank to be the same as the source rank which it is sending, then the receive, you know, kind of won't match, and then the essentially either process may hang, or even, you know, perhaps it may even receive a message from another process, and which is even worse. Okay, so you want to avoid such situations. Okay, all right, so the next thing we will see is we will look at again our maybe trapezoidal rule using this MPI send and receive, and see if we can discuss how do we calculate integration using trapezoidal rule in the context of MPI, and then maybe discuss that in the upcoming lecture. Okay, I'm going to stop here. We'll talk to you in the next lecture. Thank you.